In this video, we'll look at some more sets, or set properties, and in particular, we're going to start with an example. How many students are enrolled in Math 136, Calculus 1, or Math 226, Discrete Mathematics, or both, if there are 409 in Math 136 and 156 in Math 226? And then a question, do you need to know that there are 40 students in both courses? Well, let me go ahead and use the set notation and label some things here. So we'll put A is equal to the set of students in Math 136, and B equal to the set of students in Math 226. And then what we're after, we want to know how many students are in one or the other of those, or both. And so that's our question. But the thing is, we know that there are, so I'll go ahead and write this down. We know that there are 409 in Math 136 and 156 in Math 226. And the problem is that the 40 that are in both are in both places. Count it twice, so in order to have a count of each student exactly once, we'll subtract the 40 and come up with the number 525. So what this illustrates is the property that if there is an intersection, then the number of things in the union is the number of things in each set individually summed minus however many there are in the overlap, and that counts the individuals in the union once each. So this is a nice little general property that we'll find useful. We'll also see generalizations of it later, but keep that in mind. Some of the problems that you'll deal with use that, and of course you can do it without the set notation, but the set notation is useful to learn. So still sticking with the idea of sets, let's suppose we have a subset relationship here, and let's talk about what we mean by that. First of all, a set B is a subset of A if everything in B, so we're calling this a subset, everything in B is also an element of A. So B is a collection of things that's contained in the bigger collection A, and we call it a subset in that case, and use that horseshoe notation on the side to indicate that B is a subset of A. It's like an inequality symbol but rounded, so that might help you to remember that it means that B is the smaller. Possibly. It could be equal. Still could be equal. So there's an example here of a subset relationship, that collection right there on the left. C, F, and G are all in the thing on the right, so it is a subset. The question we have here is, how many subsets does a set with n elements have? How many subsets does a set with n elements have? So to analyze this, what I'm going to do is write out some notation for the set. So let's suppose this is set A, and I'll label its elements as A1, A2, A3, etc. through AN, like so. So it has n elements, and I'm going to consider how can we actually form a subset. And I've often used this in previous videos to talk about thinking how you would actually create one of these so you can count how to do this. And so what I'm going to think about is how to form a subset. What are the steps that I would use to form a subset? So we'll think about doing that here. And let me go ahead and get a pen for that. So the idea that I'm going to use is, will I put A1 in here? So this will be yes or no. yes or no. Do I put A1 in there? Do I put A2 in there? Yes or no? Do I put A3 in there? Yes or no? All the way out to, do I put AN in there? Yes or no? So, in other words, I can construct this subset, all the subsets this way, by, for each element, choosing whether or not to put the element in the subset. So, to form the subset, I'll have a slot argument, A1, yes or no. And there are two ways to make that decision, yes or no. A2, two ways to choose through AN, two ways to choose. And there are, in fact, 2 to the n subsets of a set of n elements. Okay, it's a very useful property. I hope that you can catalog that and keep that as part of what you've learned, because we will encounter it again. And we'll stop with this one, and the next video will take up the notion of functions.